Welcome back to our geometry series. Today we are up to section 6.2 where we will be looking at tangents. Here we have circle O. Last time we saw that a line that intersects a circle at 2 points is called a secant. Here we have secant AB. Here we've moved the line slightly, so AB only touches a circle at 1 point. And we'll call that point X. This is called a tangent. A tangent to a circle lies in the plane of the circle and intersects the circle at exactly 1 point. Segment AB is a tangent segment, and X is the point of tangency. Wait a minute, didn't we just talk about tangents? Something about right triangles and lengths of sides? Well, that's true. That relates to the trigonometric function of tangent. But here, let's just talk about geometry. Let's not worry about that right now. So here we are back with circle O and segment AB being a tangent segment. Let's add a radius of length r. And that leads to theorem 68. If a line is tangent to a circle, then the line is perpendicular to the radius at the point of tangency. So OX is perpendicular to AB. Any line that is tangent to a circle will be perpendicular to the radius at the point of tangency. And the opposite is true. That leads to theorem 69. If a line in the plane of a circle is perpendicular to a radius at its endpoint on the circle, then the line is a tangent to the circle. So one proves the other. You can go one way or the other. Let's clean that off and add point A outside of the circle. And we'll draw two segments here, AB and AC, that are tangent to the circle. And this leads to a corollary. Two tangent segments from a common external point are congruent. So AB is congruent to AC. Next, let's connect the center of the circle out to point A, creating segment OA. This leads to another corollary. Two tangent segments from a common external point determine an angle that is bisected by the segment from the external point to the center of the circle. So in other words, angle OAB is congruent to angle OAC. Next, let's connect B and C to create another segment. We've created a triangle ABC. Because AB is congruent to AC, triangle ABC is isosceles. And because it's isosceles, angle B is congruent to angle C. Those three dots is shorthand for therefore. Because ABC is isosceles, therefore angle B is congruent to angle C. Looking at segment OA and segment BC, these are actually perpendicular to each other. This is because we know that OA is a bisector of BAC, the top of the triangle. Next, let's take a look at two circles, and I've kind of connected their two centers with this dashed line. We'll create a tangent segment that touches both circles. This is what we call a common tangent line or segment, depending on what you have. It's common between the two circles. And let's draw another one. These are what we call common internal tangents. These are internal because they intersect the dashed line between the two centers. If we were to draw tangent segments that do not intersect that dashed line, kind of on the outsides of the circles, these would be external tangents. Circles can be tangent to each other. Here we have a smaller circle that is tangent to the larger circle at this 1 point. This is what we call internally tangent circles. Likewise, it can be on the outside. These would be externally tangent circles. Let's jump over the whiteboard and look at some tangents. Alright, here we go, trying to draw circles again. Let's pretend this is a circle. And we've got a nice center, which is, O. And we're going to put point out here. We're going to point P. Now we're going to draw two tangent lines. So if I had to kind of eyeball it, I'd say it's somewhere around there. That was not great. And somewhere around here. So pretend these are tangent. We'll put the tangent points in like this. R and S. And then we're going to connect O and P like this. And connect O and R like this. And this point of intersection between this line and the circle itself is point T. So let's put down some stuff that we know. We're going to say that OR is equal to 3 and OP is equal to 5. And we want to find would be what is OT, what is TP, what is OQ, which I didn't write, which is over here. Here's Q. Let's kind of connect that right now. OQ and RP. All right, so we want to find all of the measurements of these segments. So let's just write things down. OR is 3. Let's write that down. And OP is 5. So it's from here to here. So so if we put a 5 here, you might think that OT is 5. So what I'm going to do is just put one of these things. 5 from here to here. Okay. So OT. Well, OT is a radius, and so is OR. So all the radii have to be congruent. So OT, well, that's 3. Let's look at TP. Well, TP is from here to here. We know from here to here, this is 3. So the total length from O to P is 5. From O to T is 3. So from T to P has to be 2. 2 plus 3 is 5. Okay, 2. OQ. OQ is just another radius, so that's 3. RP. RP is this segment out here. Well, we can know from our theorems that this is a right angle. So if we look, we have a triangle, ROP. It's a right triangle. One side is 3. The other side is 5. So we could use Pythagorean theorem, or we know we have a 3-something 5 triangle. So this ends up being 4. 9 plus 16 is 25. 3 squared, 4 squared, 5 squared. So RP is 4. Alright, let's clean this off and do one more example. Alright, we're going to start with another poorly drawn circle right about here. Actually, that's not too bad. Let's put a good old center in here, good old O. And what I'm going to try to do is draw a tangent from here, straight up, that touches the circle and goes up like this. Another tangent out here that goes straight out. And we're going to start putting some points on here. This will be C out here in space. This tangency point is Y. This is X. What I'm trying to do is draw a triangle so that we have 3 points of tangency. Oh, that's not the greatest line ever. And let's get some more points. A, and this is B, and this is W. So this point of tangency, point of tangency, point of tangency. So circle O is inscribed triangle ABC. Now let's put down some information. So I'm going to put a 12 here. And what that means that BX is 12. Between Y and C is 6. And between A and W is 18. So the question is, what is WB here to here, XC here to here, and AY here to here? Now from the slides, there's a corollary. That's that from any given point, we have 2 tangent segments to a circle. They have to be congruent. So the distance from A to W, where it just touches the circle, is the same as A to Y, where it just touches the circle. So in this case, AY has to be congruent to AW. So AY is 18, and we can put that down here. And from C to X has to be the same as from C to Y. So XC is also 6. We can put that down here. And finally, B to X is 12. So B to W has to be also 12. So what is the perimeter of this triangle? I'm just going to draw a smaller version of the triangle down here. And we have A, Y, and YC. We have 18 plus 6. So this leg of the triangle is 24. We have 12 plus 6 for this leg. This would be 18. And 18 plus 1, that's 30. So to find the perimeter of this triangle, we need to add these up. So we'll do some quick stacking style here. 30, 24, 18, 12, 4, 5, 6, 72. So the perimeter of this triangle is 72. That's it for today. It's a pretty short video, but we'll see you next time.